for covalent bonding. This podcast will deal with molecular geometry. And by geometry, what we mean is what does the shape of the molecule look like? We're going to figure out how to do that. The theory that we use to determine what the shape's going to be is called valence, shell, electron, pair, repulsion theory. Sounds like a mouthful, and in fact it is. But we call it VSEPR for short. The key term here is repulsion. Alright, so let's take a look at what this means. So, if I have something like carbon tetrahydride, right, it's going to look something like this. What VSEPR says is these electron pairs are all negative, and because of that, they are going to orient in space as far apart as possible. Now remember, this is three-dimensional space. So the electron pairs are going to be as far apart as possible. Okay, so let's take a look at water. So in water we have two hydrogens. They each have one electron. That's 2 electrons plus 6 electrons from oxygen. We have 8 electrons to work with. To draw the Lewis structure, I'm going to put an oxygen in the center, hydrogen on each side, and then I need to add 2 pairs of electrons to give water its full octet, or give the oxygen a full octet. Alright, so if you were to predict the shape of that, you might guess it would be a linear shape. It looks just like this, like a long molecule. But in fact, it is not linear. Let's see why not. You probably remember water from your middle school days as being the shape of Mickey Mouse's face, right? There's Mickey. And so we want to look at why it is that shape. So we're more likely to draw it like this. And it has to do with these lone pairs. So let's take a look. Alright, so if we look here, we can look at what the shape of the water molecules look like. So this would actually show, it shows in three-dimensional space what the molecule looks like if we could see the lone pairs, which we cannot. All we can really see, or almost see, are the atoms. This is the oxygen. These are the 2 hydrogens. We cannot see these lone pairs. So what we'd really see is something like this. Oxygen, 2 hydrogens. And what we know are there are 2 lone pairs up here, and because they're there, they are pushing down on the pairs that have the hydrogen. So this shape is a bent shape. All we see is the atoms. Okay. So that's why water looks like a Mickey Mouse. Alright, so let's take a look at some. In your packet on page 8 is this handy-dandy chart that shows how to look at a Lewis structure and determine what we have. So let's go ahead and try using that. Alright, so the first thing we're going to draw is carbon tetrabromide. So carbon has 4 valence electrons. Each bromine has 7 times their 4 is 28. That's a total of 32 electrons. Okay, so we have carbon in the center, bromines, and of course the bromines need full octets, so I'll throw in my lone pairs. Now when we're looking at shape, what we want to do, what we're focused on, is the center atom. And the question is, how many electron domains are around the central atom? And if I'm looking at this, I've got 1, 2, 3, 4. Basically, in this case, it's the 4 bonds around carbon. So these are the 3 possibilities. Now, what I show here is this shape here has a central atom, and it's got 4 atoms around it. Okay? As opposed to this, which has a central atom, this big gray thing, like it is here and here, represents lone pairs of electrons. Okay? And then these would be atoms. So the shape that matches is this. This is called tetrahedral. I've got a carbon in the center, bromine on each side. So let's take a look at what that atom would look like. Okay, so this is carbon tetrachloride. chloride, which would look the same, really is the same as carbon tetrabromide. Now what you see is it's a perfectly symmetrical shape. On the outside, all you can see, no matter what angle you're looking at, you're going to see the same thing. You're going to see the chlorine sticking out, you're going to see the carbon in the center, and those chlorines are going to be equally spaced around. So this is a tetrahedral shape. Okay, let's take a look at another one. All right, so we're going to do the structure for ammonia. Now this is a nitrogen trihydride. Now nitrogen has 5 valence electrons. Each hydrogen has 3. That's a total of 8. So I'm going to put nitrogen in the center, put 3 hydrogens around it, give it its lone pair. Okay, so what I want to look for now, again, is how many electron domains are around the central atom. In this case, the central atom is nitrogen. So I have 1, 2, 3, and 4. Notice the lone pair counts as an electron domain. Okay, so what I have is 4 electron domains. So again, I have the same 3 choices, right? And in this case, I have 3 atoms. 3 atoms, 1, 2, 3, and this unshared pair like I have up here. So this shape is trigonal pyramidal. So let's take a look at what that shape looks like. Alright, so let's take a look. What we've got here is, this is NH3, okay? So if we were able to see the lone pair, this is what it would look like. The electron pairs are equally spaced around that nitrogen. But of course we don't see the lone pair, and this is actually what we see. We see this, what's called a trigonal pyramidal. It's almost like an upside down pyramid, okay? With a lone pair of electrons sitting up here. Okay, let's go back and take a look at what else we have here. Alright, we have H2S. Alright, we have 2 valence electrons from hydrogen, plus 6 from sulfur. That's 8 electrons. We can put sulfur in the center, put the hydrogens around it, and then sulfur needs its lone pairs. Okay, so what we have, how many domains? We have 1, 2, 3, 4. Alright, again, we got the same 3 choices. In this case, we only have 2 atoms attached, 1, 2, and we have 2 lone pairs. So this shape is going to be bent. So let's take a look at the actual bent shape. Alright, and we have H2S. And this is what H2S looks like. Actually, it looks just like H2O. Okay? If we could see the lone pairs, what we would see is something that looked more like this. Equally spread apart electron pairs. But this is all we see, because we see just the atom. Okay. Let's take a look at carbon dioxide. Now, carbon has 4 electrons. Each oxygen has 6 for 12. So that's 16 electrons. Okay, so I have carbon, I have oxygen, and this is going to end up having 2 double bonds. Okay? That's the structure, Lewis structure for carbon dioxide. Now I want to count the number of electron domains around my central atom, which in this case is carbon. This double bond counts as 1 electron domains. Alright, this counts as 1 electron domain, so I have 2 domains. So in this case, there's only one choice. This is a linear molecule. Carbon in the center, oxygen on each side. Alright, so let's take a look at CO2. Alright, this is what CO2 would look like. It's pretty rigid. It's got a carbon in the center. It's got 2 oxygens combined to the carbon by a double bond. Linear structure. Okay, so at this point, what you should be doing is completing the examples on page 7, using that chart, the shape chart that we were just looking at that's on page 8. And then once you've done that, I'd like you to go back to page 6 and identify the shape of each molecule.